Working on electronic equipment has many hazards associated with it that can cause injury and/or death. Please do not work on energized equipment unless you take proper precautions. Working on such equipment is done at your own risk and not at the prompting of information from this or any other YouTube channel.
Hello and welcome back to Poor Man's Electronics Bench. In this episode's part 3, I am going to cover some background information on the Eico 443 semiconductor curve tracer. I found out some information by doing some research online about the unit. I was kind of interested slash questioning whether the power transistor setting drive signal was actually supposed to create 4 curves in the family instead of just 1 as my unit is doing. As it turns out, if when correctly functioning, it is supposed to generate 4, and I've noticed that also from multiple sources of information. I was just going to take you through some of the stuff I found about this particular unit that's interesting. It took a little computer time sitting on my arse and just surfing around doing some searches and researches on equipment from this period. And one of the first things I found is interesting was an old ad from Eico. It was makes it possible for most general purpose oscilloscopes to display direct readouts of the most meaningful data. And it says diodes, rectifier signal and power transistor characteristics can be tested by the versatile model 443 curve tracer. Circuit designers and service technicians will find invaluable for determining the DC characteristics of a wide variety of silicon and germanium semiconductors. The output of the 443 can be displayed on most general-purpose oscilloscopes. Diode and rectifier characteristics that can be tested include forward voltage, forward current, reverse current, and peak inverse voltage. The PIV test voltage is variable from 0 to 1400 volts. Transistor tests included those for HFE, HOE, ICEO, VCE, saturation, and BVCEO. And other significant features of the Model 443 are all silicon solid state printed circuit construction, which isn't totally truthful because a lot of it's point-to-point wiring off the switches, the majority of the hard stuff anyways. Dual transformers for isolation and safety. Flashing lights indicate high voltage and at diode test terminals. Matching switch for comparing and matching transistors. Direct reading beta control on front panel. Built-in oscilloscope voltage calibrators. Terminals for connecting external test sockets. And it gives all the specifications on the unit. And it's an interesting ad that gives information on here. I'll leave this up for a little bit. I probably should have zoomed in when I read it, but this is exactly the particular 2 devices that I have. And I will link all of this web information. Well, this one I can't link. I forgot where I found this particular ad, so. But it's the general information is out there. It also can be found in the downloadable manual on it. So it's just interesting. The age and time period of this unit I found is actually right around 1971, and I ran into that information from browsing through various sites and looking for some information on manuals from that current vintage of time. And in this instance, I managed to stumble upon the worldradiohistory.com website, which I will also put a link to. And they have a section on the website called PF Reporter, which is Photo Fact Reporter. It was a Sam's magazine that was issued for people in the industry, technicians, possibly some engineers if they were interested in some information, owners of particular businesses that might be involved in the servicing of equipment such as this, and all the all the electronic test equipment and different methods, and just a slew of information on troubleshooting stuff. Some of the stuff is quite interesting. I didn't go through it all by any means because there's a lot of stuff to go through. What I ended up doing was searching around through my year, and they're searching around through a year of time where I thought that this unit might be available, and I found out some information on curve tracers in 1971, February and March. In the particular one for 1971 February, they had an article on page 38 of the PDF, the downloadable. These are all in downloadable PDF files as well. So they had an article on the curve tracer, another method of testing transistors. And in this article, it features a Judd Williams Model A transistor curve tracer. Mostly talks about that and the different ways it can be used on different devices, how a curve, basics on how a curve tracer works. This is just basically a 2-lead component tracer setup, but they do have a simple, a lot of little schematics and just a value of information in these magazines and magazine articles that these authors made. And it shows a little picture here on this particular curve tracer and the what would be considered the staircase signal between the base to collector that turns the transistor on. And most curve tracers do use a progressive step staircase signal to generate the drive on the base, which ends up being the vertical axis. And on the horizontal axis, it could be something that is as simple as driven from a tap on the 60 hertz transformer, power transformer someplace, or another smaller transformer, or it could be an internal sawtooth or triangle wave generator to drive the horizontal to create the curves. But it goes into the basics on two signals that are applied to the transistor and how they are translated into the signal you see on the oscilloscope screen, and how to read the different signals and see what type of issues you might have with the transistor device under test. So there's about a 6-page article on this one or so. It's a lot of information and fairly in-depth. It's just the basics on a curve tracer, but it's very good. Most of this information is found in the manuals on curve tracers themselves. If you go to like a Heathkit IT 1121 or 3121, gives you a pretty good view and indication of the different screens you might see and what that might mean as reading them to determine the condition of the particular component under test that you have on a device. So this is the February 71 issue. Now in the March 71 issue, I do have, I gotta find it, I got a page up here somewhere. Oh boy. No, that's the catalog page. I'm gonna go to the website here and download it again. March 71, and in this case on page 2 they do have a little Eico catalog. The nice part is once you get to these pages for these PF Reporter, they have usually ads on the current new releases of the particular devices that are being sold at that time. And this in March 71, this shows the Eico 443 curve tracer. And in this magazine in particular, on PDF page 64, if I could jump to that, it has an article called Practical Application of Transistor Curve Tracers. It's made in a book view. So these are 2 consecutive months with information on curve tracers. So apparently people are finding them at the time a handy and possibly worthwhile to have device on their bench. If you notice here, this is Shop Talk with Carl Babcock, ES Technical Editor. So this is practical application of transistor curve tracers, and going through there, it has a lot of the same information. In this instance, it's showing what some things might look like if you're looking at an in-circuit component. It covers some talk about the Judd Williams curve tracer as well, and again it shows the sweep and the staircase generator signals from that particular device, and some of the signal outputs. And then on page 68 it shows the Eico 443, and it gives some talk starting in this paragraph or chapter about things. And the one thing I notice about it that I definitely have to agree to is one strong feature of the Eico 443 is the accurate series of tests for diodes, including reverse leakage, maximum peak inverse voltage, and voltage drop in the forward direction. And one thing that it's also handy about this unit, handy and not many other units can do, is the fact that you can use that peak inverse voltage to check for a premature or faulty breakdown voltage level in a transistor as well, just by testing between two junctions instead of hooking it up to the curve tracer itself, because this only has a drive signal sweep of about 40 volts maximum, and it won't stress a lot of modern day power TO3 power transistors for a lot of amplifiers. But using that peak inverse voltage function, you should be able to find any breakdown fault leakage in a junction that you normally wouldn't, even through some other components that only drive up to 200 volts. Driving something up to 1400 volts is past most of the breakdown voltages you're going to find on most transistors. And it goes into in depth about using this one. But one thing I noticed also about this article, it says the Eico 443 is available in either kit or wired form. We built our sample from the kit and encountered no problems. The tracer worked on the first try. And I was looking for any information about a display of a power transistor. Now, I didn't see a lot of the small signal traces that show a family of 4 curves, and I was just wondering in general, but they didn't specifically, I don't know if they specifically showed any traces. They also had some information on using the diode test function on this as well, testing diodes. I was looking for something here. Power transistor, excessive leakage is indicated in these tilted curves of an NPN power transistor, and the beta tested only 25, but this does show that unit set to the power transistor position should generate a family of 4 curves. So that is information I was definitely looking for. And then the cherry on the cake is to try to find some information on this unit currently in the wild and in use, and I managed to do that because on a fellow YouTuber's site by the name of Ray Gianelli, he actually has recently used one of these on his bench. He's done some testing on the power output transistors for a Sansui AU919. He was nice enough to show the particulars of the testing. I'm going to leave a link to this particular episode in my notes as well, so if anybody's interested. And Ray is probably somebody to watch if you're in the need or want of knowledge for troubleshooting. I found the site is supposed to be very informative, and seems to be a good presenter, jovial enough. And here he's showing also as well a power transistor. He turns it on and there is a family of 4 curves coming out of that unit. So I definitely know that properly functioning, that Eico 443 should be putting out a trace similar to this with Howard transistors, not just the base and the top trace, which my unit was doing. So going forward, I am going to go through the troubleshooting and fix for that particular issue, and then get back to the finality of doing some other repairs on it. There's another small repair I found I'd like to do. It has to do with the flashing bulb function for the high voltage peak inverse voltage test. This particular light bulb is supposed to be illuminated and flashing at a visible rate when you have this energized for peak inverse voltage, which could be up to 1400 volts. And the issue with that is it's on, but it's not oscillating at a frequency where it's detectable to the naked eye. And even though I've replaced the factory components with stock values that are in tolerance, it's not oscillating properly. So we're going to go over the adjustment to get that to work properly. So we will go into that following the rest of the information on this episode. And welcome back to the repair work on the Eico 443 semiconductor curve tracer. This is my unit number 1. This was my factory built one. As I was mentioning earlier, this one has one kind of major issue with the curve tracer function for the power transistors. It does not want to display a family of 4 curves. It's only displaying one, and it's something that needs to be addressed. I think I found the issue, but I'll go over with you how I found it. It was basically through passive component and continuity tracing using an ohmmeter, just then studying the schematic. And schematics help a lot doing work like this, and I'm going to go over share what I did with you as far as working on the schematic. I managed to get a copy of the schematic from the source online, and unfortunately it was chopped up in 3 parts of a PDF or a mosaic format, and I took the extensive time to join everything in, to do a lot of work on putting component values and names into certain positions so I can recognize what the heck was going on with this thing. Some of the switch labeling I have on this schematic is kind of fuzzy still, but if you printed this particular schematic off, this would be about 20 by 30 inches actual size, just because it's kind of hard to read. And the nice part about a computer is, yeah, you can zoom in on it and take a look at things, and this is mostly what we're going to be working on. But then what I also did was I took the time to sectionalize just the components involved in the curve tracer signal generation and distribution back to the outputs for the oscilloscope. And that looks a lot like this. It's basically a lot smaller, a lot more condensed, easier to read. I got rid of some of the point-to-point wiring and the switch configurations in this in order to just make things less confusing for me. So I'm going to go over what's going on a bit. First off, we have our signals for our NPN and PNP transistor testing. The drivers are 2 different groups here. These are for the signal level. And what happens is this section actually takes, and I gotta stop using the word actually, I know. This section takes the power section, I should say, takes the same drive that goes to the base
of the signal level transistor connections. Once you put your transistor, hook it up to the unit, however you do, and instead of putting it through a transistor and putting it back through the oscilloscope for your vertical and horizontal, it takes them and puts it through another level of amplification using the same type of transistors that are in the section that creates it. And there's really, besides this 5.6 ohm resistor, and maybe off, let's say off of the, in this case they take the collector drive off Q5 here, they put a 5.6K resistor in it. On this one, there's on the PNP they take a 5.6 ohm and put it to Q3 or Q4. So it's basically the same thing. It's just I mislabeled this. This is actually the PNPs and this is the NPNs, the way it's connected. Or I labeled these wrong, one of the two. But regardless of that labeling, I'll try to figure that out and make sure I get that right later. I'd like to also take, well, these notes are not on the schematic that I made together off the mosaic, but I'm just going to keep this viewable for the troubleshooting that we're doing in this case. So really, for the first level of signaling, if we're going to test our NPN transistors, the base of Q5 is going to just go through and be connected to R31, and then it's going to, the collector of Q5, and then that's going to go to the base of R7. And I'll have to jump back and forth between the schematic and the view for the Eico unit. I left this board unmounted for right now just so it's easier to get to some of the stuff on it. And going to set up a meter. I may or may not use this in continuity mode. We'll see what happens here. Probably, I don't know if I can keep this thing visible on camera. Maybe if I scooch this guy over I can. There we go. And we got a good continuity test. Now we're looking to test. We've got it set for NPN. So that means my collector from Q5, and it's kind of hard to, although the board is marked fairly well, I'm going to try to connect to the transistor first, then I'll zoom in. Q5 is the lower. It's nice that they have the top of the board stenciled fairly well. The collector of Q5 should go through, if we switch this to power, signals in that switch position, and the switch is over here, power is in that one. If we switch that to power on an NPN, that collector should go through to the base of Q7 through a 5.6 kilo ohm resistor. So I'm going to locate Q7's not too far away from that one. It's off to the left of the view screen there. So that one should go to and have continuity through a 5.6 k ohm resistor. It does not. So that connection is suspect. I hope the outside noises aren't bothering things too much for the video. I have a lawnmower from a landscaper running in the background, but in the meantime I'm going to try to pursue further investigation into this. And what I am finding out is that Sometimes having an accurate schematic can be worse than having no schematic at all, because at least with no schematic, that will force you to sit down and do signal tracing and or continuity tracing through components, through resistances, as well as you can to find out your signal paths. When you have a designated schematic, you are expecting the markings for the components as well as the values to be accurate. And in this case, I am finding that that is not the case at all. What I have done is, outside of the schematics that I personally manipulated, I went back to, or I downloaded them from, it was the Boat Anchor Manual Archive, the bama.edebris.com, which has a lot of information for a lot of devices on here. And in this case, this file is available as a Deja Vu, very compressed file format. And I have a reader for those installed into Chrome, so I can download and look at those without any trouble. Although it's compressed, once it zooms in, it's a fairly clear picture of what's going on. And towards this is just the user manual. This is not the actual service manual, but what it does have is a 3-section mosaic of the full schematic, which is what I pieced together in order to get my full schematic. And one of the first things I was doing was I was checking the component markings on the transistors to make sure they match from what, because I did relabel some of this stuff because it wasn't too legible here and there. Some of the stuff is like Q1 is missing the 1 and stuff like that, and this is, well, it's barked. See, like this is a 0.47 orange, I put an orange drop capacitor in there, that you're missing your decimal point. A lot of stuff like that happened on this scan. And I was just going to look over here. Q5, you've got Q5, Q6, Q1, and Q2 for our staircase generator transistors for the signal level. So Q5, Q6, Q1, and Q2 are paired. And in the schematic that I made, that's what I have. Q5, Q6, Q1, Q2. Now, associated to Q5 and Q6 is capacitor C3, which is supposed to be a 300 microfarad 25 volt electrolytic, and then capacitor C2 is tied to the base of Q6 directly. That is a 0.47 UF orange drop. Now let me zoom in and show you what I found on the markings on things. On the left side of the board there, you'll see capacitor C3. The capacitor is right on top of the marking, so you can't see it in that case. And this is capacitor C2. And I know that's the case because the other orange drop capacitor next to it is marked, you can see it's marked C4. So these two capacitors, and then there's C5 is the other electrolytic. It's in relation to it. It's right underneath it. So these are definitely C2 and C3. And in the case of the capacitor C3, that has its positive termination connected to the collectors of Q5 and Q6 through a 5.6k ohm resistor on either point. And here's where the miscommunication and the misdirection lies. Right adjacent to C3, the two transistors that are there, if you look at that one says Q3. I don't think I can zoom in. No, I really can't zoom in anymore from this distance. That's the best one I got there. And the other transistor is Q4. Off to the left here. You got the focus going on there. The other one's Q4. So they're totally mismarked from the schematic to there. And I know that for a case because I can go to the I've got my own meter set up, and I will go to the collectors on both of those transistors. I'm going to go to Q4 first. The collector connection's on top. It's a little hard to get to, but always working on stuff is always fun. You find a way somehow. There's the collector connection. If you look at my meter, I got 5.6 kilo ohms. And Q3, same deal, 5.6 kilo ohms. And there's no way that that's going to go through to 5 and 6, because 5 and 6 are all the way down, are marked all the way down on the bottom part of the board here. These are actually the drivers for the power transistor test. The signal from the collectors on these goes to the signals on the bases on one of these two. Maybe these, maybe those. I'll have to check that, but I'm going to have to go through the schematic and do a bunch of continuity tracing and relabel a good version of the schematic just to get the proper continuity and signal path through everything, just because somebody didn't pay attention to all of the little markings between the board and the schematic that are supposed to match up in order for somebody to have a working and effective schematic. So I'm going to pursue some of that. I'm going to correct the two schematics that I made to the best of my ability. I've got to go through all the transistor connections, make some notes, and then go through, correct my schematics, and then go forward from there. So I shall return in a bit. And moving along and getting in and along on things, I discovered a couple of things. First off, the little view of my sketch pad here. On the schematic, I have found that the schematic to the board, my NPN's Q5 on the schematic is actually marked Q4 on the board. The schematic marking Q6 is actually Q3 on the board, causing a bunch of chaos for some continuity tracing. Q1 and Q2 are correct, and looking back on the schematic that I have, since Q1 and Q2 are correct, I am trying to look and see where they're tracing out to. And in this case, the collector of Q1 should go through a 5.6 kilo ohm resistor and go directly to the base of Q3. And if you look, that's what I have my meter connected to. I have the collector, I can't see the number there real well, but I don't know, I'm wrong. On the bottom there, it's actually marked Q6. I'll take it off. Yeah, that one's marked Q6, and then the one next to it is Q5. So it is looking like what should be tracing that schematic portion out, what should be Q3 on the schematic is actually Q6 on the board, so I have to note my pad for that. Q3 schematic, Q6 on the board. So in that case, I should be able to do the same with Q2. I'm going to go Q2 collector, and that one should continuity check through a 5.6K resistor. Notice the meter's showing 17K, so that's definitely not a direct path. That one should continuity test to the base of Q5, which is the one all the way down in the lower corner. And there we have it. So that solves part of my continuity checking dilemma. I was really wondering what was going on, because I was sitting here for about an hour trying to get this continuity values through these resistors properly, thinking I was going insane, something was going wrong, and then I finally just kept on poking away at it until I finally got the right connection paths on everything, and lo and behold, discovered that the markings were bad. I'm going to say they're bad on the schematic. It's hard to really blame the silk screen. It's easier for me to change the schematic than it is for the silk screen, and seeing that the silk screen is manufactured, put out in the market and into units, and you can change the schematic markings easier. I'm gonna re-stencil the schematic. One or the two are wrong, sure, but somehow or other the thing got built by the factory, put together, shipped out as a working unit, and I just have to find out the rest of the faults in the unit in order to get all the functionality out of it. So I'm going to continue to work on that and see what else I find. Well, I tell you, I was having some brain issues from trying to figure out all that stuff with the schematic, and as it turns out, I ended up making a little videography mistake, and the dog ate my homework, and I did not record the part where I discovered the fault. Now, I can't say that I did discover it a couple weeks ago when I looked at it. It was something that was a little obvious, although it was hidden from plain view. And what happened was I figured it out through the signal tracing, through the continuity tracing. But all these little wires that go to this printed circuit board are going, a lot of times it's taking a connection off the board, bringing it to a switch or a potentiometer or a rheostat, and then bringing it back to the board. And what was happening, because the final connection on the board for the output is actually, oh, stop saying actually, damn it. The final connections are direct connections through the board through hardware to some banana binding posts on the back. And in the case of the missing traces on the curve, the wire, there was a black wire going to this terminal W here. It's out of this harness. That was broke right at the board. Somebody in the manufacturing most likely got a little enthusiastic and quick with the strippers when they went to go strip that wire to make the connection, and it just, through a little fatigue of moving around a little bit and me being in there replacing components. Now, considering the fact also that I did not test this before I started, I decided to shotgun it. And it's kind of funny because thinking about it, even though I just didn't find any faulty components, just replaced things with new or intolerance components. But if I did test it beforehand and found it to be working, shotgunned the parts in and checked it again and saw the fault, I would probably be chasing my tail going over all of the components I put in, trying to figure out which component I put in wrong. Whereas it turns out I double and triple checked all my component installations, so that wasn't part of my fault finding process. It just got to the point where, let's start checking continuity using the schematic, and then compounding on top of things. The schematic was leading me down the wrong rabbit hole. So finally got things figured out, got to the point where I can visibly see that fault and do continuity tracing through it to get from the collector connections and the signal transistors to the base drivers for the power transistor driver was what I needed to do. And once I finally arrange the proper positions of the transistors to the schematic, it all made sense again. So I'm going to put this thing back together and show hooking it up to the oscilloscope and show some testing. I am back, and it took a crap load of setting things up and adjusting on this guy. It's because they have a dedicated scope. Right now I don't yet, and also I've got a digital scope, and digital scopes do not work well with old school analog curve tracers. Since the persistence on the trace and the sweep and everything, especially if you put it in XY mode, it's leaves something to be desired. But it looks like there are a family of 4 curves. It's just that due to the sweep rate and the triggering and everything, just looks funny. Huh? Give you a little close-up look on it. And it's upside down, but that's a properties of this. I could probably invert. Let me see if I can invert this particular. I take the invert off, that would work. Menu off, then I've got to reposition my waveform because it's gone totally off screen. So this looks more like a normal trace. And what to do for calibration too is there's a switch on the unit on the bottom, put a calibration signal on, and according to the instructions you're supposed to have a line that is 8 full gradicules high by 5 gradicules across. So I can adjust to that, and what that should do is allow me also to work with the calibration on the knob on the unit to extrapolate the gain on that particular transistor for the drive that's on it. Now we've got 1, 2, 3, 4, 5 by 8, so that's I don't know how the horizontal position is going to work, but I'm going to go and click this guy back in, and if you notice there is 1, 2, 3, and 4. There's 2 of them tight going back and forth, and they're not progressive because of the manner of the stair step signal design on this. I think I showed you earlier. It's not a progressive step up in voltage. It's the steps kind of alternate levels and weird progression, but you don't notice it as much on an analog scope. So in this case, I can take the power adjustment knob on the unit, which is this one here, and in order to figure out what your gain is supposed to be, you adjust it so your sweep goes the full 8 vertical gradicules. And in this case, on this unit, it's about just above the 140 line. And I have 2 transistors in here. These are pulls out of, I think, some Dynaco ST120 amplifiers. This one is one of the audio output drivers, and I believe this one might be for the power supply, which is supposed to be a very low gain transistor. So I'm going to switch over, like 20 or 30 max. I'm going to switch over to that one, and if you notice, the sweep on the scope definitely is telling me that there's a large difference in gain. So I'm going to, oh, maybe I'm wrong. Maybe the gain is higher in this one for some reason. Got a gain of about, on the knob is about 160 or so, and it's also a little, signal's a little funny as far as it's like some oscillation there on the drive and the sweep. I don't know what that's all about. It could be the transistor, it could be the unit or the coupling to the scope. Things are maybe maladjusted. Out of curiosity, I'm just going to put this back in the calibration position here. I'm going to take a little cheap transistor tester and test these guys one at a time just to see if this unit actually measures something resembling gain that a more standard tester might come up with. Seeing that this is such an old unit, it's early 70s. It's more going to be for letting you know if the part's working or not, and really to drive it to its peak inverse voltage. It needs to be hooked up in the diode test section on this. So the nice part about these guys is it don't matter what lead goes where. This one says 227 gain. And let's see what this guy exposes. 59. That's kind of weird. It's actually opposite of what the reading for the gain on the knob is, and I was kind of wondering about that. It seemed like the way it's configured, it's inverse to what you would think a normal gain setting would be, and I wonder if there was a factory wiring mistake on that as well. Always that possibility. Yeah, because this one's still measuring over 140. There we go, I had a bad contact on it. This one's saying it's got a higher signal gain. This one's saying it's lower. But it's definitely testing the A transistor if you pull it out, so kind of a mystery on that part of it, but at least it does tell me that the transistor is being tested, for one. For two, it is generating the 4 traces you'd like to see, the 4 family of curves you'd like to see in a test. So that one open connection that I did the troubleshooting and repair on definitely seemed to make a difference in the performance of this unit. So my last thing to troubleshoot is my peak inverse voltage indicator lamp here. And it's a darker out. I can probably show you that. When you turn on the switch for peak inverse voltage, you were supposed to get a flashing glow of the lamp. Now if you see the 2 lamps, this one's, the power indicator is definitely a lot brighter, for one. For two, and it leads me to believe that although this does have an indication, it's might be oscillating so fast that it's actually cutting down the voltage. And I'm also not sure of the shape of this bulb. I'll have to do a lot of investigation on it, so I'm basically going to have to turn this thing over, gut that whole circuit, maybe breadboard it, and I can use my Eico 1140 substitution box to do some in-circuit variables while it's live, in order to try to figure out what's going on with it. I just would not like to run into any problems. And maybe after I do that, I'll go over using the peak inverse voltage function to do some breakdown to see what voltages these 2 transistors might break down on their junctions for a peak inverse. So that will be the next part of the video. I've decided to end this episode here because it's run almost an hour, and I'm going to take more time to work on that flashing light oscillator. And also, I am going to try something. I have the adjusting potentiometers for the power transistor gain, and I double checked the wiring on them. They have one design part to them is they don't have a connection on the double pole potentiometers. They don't have a connection on this one pole here, and the way it's behaving, the potentiometer is almost behaving like it's backwards. And even though the wires are in the correct place according to the schematic and the parts diagram for the kit, which I do have, I'm going to try moving the wires off of these two sides and experimenting, moving to here, and maybe that would change my measurement value or setting value between those two power transistors. Because remember, the one that was definitely, that transistor is definitely supposed to have a lower gain, and it had a higher gain according to the knob. That didn't make any sense at all, even though we were measuring things AC with a curve tracer, and the DC gain is going to be similar. It's not going to make such a big bold jump over a amplification transistor. So I'm going to try that out of my next part to this, and hopefully the next part will be the final. So I thank you for viewing. Please feel free to like and subscribe, especially subscribe if you'd like to see more content like this, even though it's drawn out and long-winded. I tried to just cover some things, even though it's some older vintage stuff that there's not a lot of information for on other videos or out in the internet as far as seeing a working piece of equipment. So until the next episode, take care, and I hope you will return soon. This content is available on YouTube and Odyssey.com. If you enjoyed this, please like and subscribe. Hope you return soon.